In this video, we're going to go through the entire Unit 1 study guide. Let's do it. All right, number 1, analyze the following notation systems. So, you'll see atoms and ions written in this form. Let's go through and let's identify what everything is. So, A, upper left-hand corner, that's the mass number. Okay. Down below, Z, that is the atomic number, which is also equal to the number of protons. Atomic number, which is also number of protons. All right. Let's see, X. X is going to be the element symbol, like hydrogen. Whoops, like H for hydrogen. And then B, up in the upper right-hand corner, that is going to be your charge. All right. So with that in mind, let's move on to B, C, and D. Okay. So here, we know down here, Z is 35. That's the number of protons. Our charge is -1. So that means we have one more electron than proton. So 36. And then our mass number is 80. So 80 minus 35 is going to give us our mass number, it's going to give us the number of neutrons, which is 45. Okay, moving down to C. 12 is the number of protons. Again, that's coming from down here. Plus 2 means we have 2 more protons than electrons. So we'll have 10 electrons. Our mass number is 24. So 24 minus the number of protons gives us 12 neutrons. All right, this one's written a little different. This right here is your mass number. Okay, so we're going to have to do this a little differently because it's telling us carbon 14. We just know the mass number. So if we go to the periodic table, carbon is number 6 on the periodic table. Okay, so let's fill that in. If it is written in this form, we know that there is no charge. So the protons and electrons will be equal. We know the mass number is 14. 14 minus 6 is, I can't type today, 8. So 8 will be the number of neutrons. Okay, what is an ion? So an ion is an atom that has gained or lost electrons and has a charge. So another way of putting that is different number of protons and electrons. They can't be the same. So for example, this would be an ion because it has a +2 charge. This would be an ion because it has a -1 charge. Carbon has 6 and 6 in this example. So it would not have a charge. It would be an atom. All right, positive ions lose electrons, and they're called cations. An easy way to remember that, cats have paws, right? Cats have paws. Cat ions are positive. See what I did there? All right, negative ions gain electrons and are called anions. All right, isotopes. Isotope is 2 or more atoms of the same element with the same atomic number, same number of protons, but different mass numbers. So same number of protons, different number of neutrons. So let me give you an example. Carbon has 6 protons. So let's say I had carbon 12 and carbon 13. So they're both carbon, but they have a different mass number, so they're going to be isotopes. All right, let's go ahead and fill in our table here. Okay, protons are equal to the atomic number. Chemical symbol So let's pull up our periodic table again. It has an atomic number of 29. So we want to find 29 on the periodic table. That's copper, Cu. Okay, so Cu. Okay, it has 29 protons. It has a mass number of 65. Okay, what else do we know here? Well, we can subtract to get our neutrons. So 65 minus 29 is 36. We have 28 electrons and 29 protons. So that would mean that we have one more proton than electron. So our charge will be +1. This will be a cation with a +1 charge. All right, the next one, atomic number 7. So it'll have 7 protons. Let's see, we know it's an anion, so it's got a negative charge. That means there's 3 more electrons than protons. So we'll have 10 electrons. The mass number is protons plus neutrons. 7 plus 8 gives us 15 here. So I would need to go to my periodic table and find number 7. Number 7 is nitrogen. Okay, so atomic number 7 for nitrogen. The mass number is 15. And the charge is -3. Okay, third line. 22 is the atomic number. So that's going to be the number of protons. 22 protons, 20 electrons means we have a cation with a +2 charge because there's 2 more protons than electrons. Mass number is protons plus neutrons. So if we know the mass number, we can subtract the number of protons to get the number of neutrons. 46 minus 22 is 24. And then we would need to look up number 22 on the periodic table, which is titanium, Ti. So 22 is our atomic number. 46 is our mass number. And then our charge is +2. All right. Let's fill these in. Atomic number for my 4th row is 33. That'll be equal to the number of protons. Our charge is -3, so it'll be an anion, -3. -3 means we have 3 more electrons than protons, so this will be 36. Okay, now we know the mass number is 75. 75 minus 33 gives us 42. Oops, that should be 42. All right, down here, 19 will be our atomic number, which is equal to the number of protons. It tells us our charge is +1, so that'll be a cation because it's positive. +2 means we have 2 more protons than electrons, so that'll be 17 because we have 2 more protons than electrons. Mass number is 39. To get the neutrons, we can subtract. So if we know the mass number, we can subtract the protons, and that'll give us the neutrons, which are 20. All right, moving right along. Number 5. Analyze the following models of oxygen. Mass number, protons, neutrons, electrons, and then is it positive, negative, or neutral? Okay, this is our mass number. Protons in oxygen, okay? Can't really count them from the model, but if I go and look for oxygen on the periodic table, oxygen is number 8. Okay, if the mass number is 16, 16 minus 8 would give us the number of neutrons, which is 8. Electrons we're going to have to count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we have 10 electrons, 8 protons. So this will be a -2. So it'll be negative ion. All right. Now, be careful here, because this one's oxygen 16, so is this one. So the mass number is going to be the same. Because they're both oxygen, it'll have the same number of protons. It'll have the same number of neutrons. But you can already tell that we have a different number of electrons. Let's count these up. 1, 2, 3, 4, 5, 6, 7, 8. This will be neutral. 0 charge. The number of protons are equal to the number of electrons. All right, here's oxygen 17. So oxygen still has 8 protons. 17 is the mass number. If we know the mass number and the number of protons, we can subtract, and we will end up with 9 neutrons. 17 minus 8 is 9. Now let's count electrons. 1, 2, 3, 4, 5, 6, 7, 8. This will be also neutral. Okay. Number 6 says, how would you describe Model 2 and Model 3? What's similar? What's different? Okay, so we're looking at these two right here. Well, they have a different mass number, so they're going to be isotopes of each other. 16 and 17, okay? So they have the same number of protons, different number of neutrons. They're going to be isotopes. They have the same charge, so they're both neutral. So the only thing that we can say similar, same charge and same number of protons, different mass number, different number of neutrons. All right, number 7, are they isotopes? Yes or no? Okay, both of these are magnesium. This one's 24, this one's 25, so yes. Fluorine and neon. They have the same mass number, but they're not the same thing. They're not the same atom. This one is 9, this one is 10, and obviously fluorine, neon, no. Okay, 6 protons. 6 protons, that checks out. 6 neutrons, 8 neutrons. So same protons, different number of neutrons. This is absolutely an isotope. 20 protons, 20 protons, 20 neutrons, 20 neutrons. No. They would have to have a different number of neutrons. All right, moving right along here. Number 8 says element A has 3 isotopes. One with a mass of 225, an abundance of 20.04, and a mass of 225.11. Another is got a mass of 226.10, and it is 45.23% abundant. And the final one has a mass of 228.11 with an abundance of 34.73. Okay, first things first, most importantly, always convert percents to decimals. Okay. Our formula is also average atomic mass is equal to mass times abundance plus mass times. You just keep doing that for as many isotopes as there are. In this case, we have 3. Now, to convert our percents to decimals, we can divide each one by 100. So for my first isotope, its mass is 225.11. I'm going to multiply that by its abundance as a decimal. So 20.04 divided by 100 is 0.2004. Now I add that to the next one. My second isotope has a mass of 226.10 and an abundance of 45.23. Again, divide that by 100. Okay, and I have one more. Our final has a mass of 228.11, oops, 0.11, and an abundance of 34.73. Again, divided by 100. Now, when I enter this in our calculator, we want to use parentheses. Okay, so just be careful when you enter it into your calculator. You should get a value of 226.6 atomic mass units. Okay, 9 and 10, and then we have some models of the atom. Okay, so for 9 it says calculate the average atomic mass, show all words in units, then identify the element. Okay, so this one's different because it gives us a remainder. We know our percents have to add up to 100. So I can subtract from 100 minus 19.9% equals, what is that, 80.1%? Same thing. We need to convert our percents to decimals. So same formula. So I'm going to take the mass of the first isotope, which is 10, and I'm going to multiply it by its abundance as a decimal. So 19.9 divided by 100 is 0.199. Do the same thing with the second one. Isotope 2 has a mass of 11, and I'm going to multiply its mass by its abundance. 80.1 is going to be 0.801. And then again, just put it in your calculator. You get a value of 10.8 AMU. Now, this question is different because it says identify the element. So let's pull up our periodic table, and we want to find the element that has the closest match to 10.8. Let's see, 1, 6, 9. Oh, look at boron. Boron is 10.81. That is like a perfect match. So our value here would be boron. All right, number 10, same concept, just more numbers. So to get isotope 4, which has a remainder, let's subtract from 100. So we're going to subtract out 3.41 minus 20.91 minus 25.16, and we get 50.52%. Same exact format, mass times abundance for each isotope. So for isotope 1, its mass is 204. I'm going to multiply it by its abundance, and this is where you would probably want to divide by 100 instead of move the decimal place, because a lot of people make mistakes if the abundance is less than 10. They always forget to add that 0 in front. So it'll be 0.0341. Isotope 2 is 206 times 20.91 would be 0.2091. Isotope 3 is 207, and it's 0.2516. And then the remainder is 0.5052. You know what I forgot? I forgot to put in 208. 208 times 0.5052. Okay. So I'm going to get an answer of 207.2. Now, one thing that I want to point out when you're doing an average. So, like, I almost made a mistake. I almost forgot to include my 208. So if I had done the math, I might have gotten a number. I'm just going to throw out a number. Let's say I got an average of, I don't know, 187. Okay. How do I know that that number is reasonable? Well, when you're doing an average of something, your average value should be between the lowest number and the highest number. So if my average was 187, that is not between 204 and 208. So that would be no good. The answer that I did get was 207.2. So that is between 204 and 208. So that would be an acceptable answer. So now we want to find on the periodic table which value has the closest match to 207.2? Oh, look at that. I have an exact match here for lead, 207.2. So my answer here would be lead, Pb. Oof, why is that yellow? There we go, lead. All right, let's move down to models of the atom. Oh boy, we have a lot going on here. All right, so for the first model, describe one thing that fits accurately with your understanding of the model. Well, let's see. It has positive and negative particles. What doesn't fit accurately with your understanding of the model? Well, I don't see a nucleus. Say missing nucleus. Missing neutrons. No orbitals for electrons. State at least one way in which it can be improved on the model. Well, there was no model before this one, so we need a nucleus. All right. So add a nucleus and move the positive particles to the nucleus with the electrons around it. Okay, so let's move on to this next one. This one looks a little bit better. So one thing that fits. Well, let's see. We've got positive particles. We have a nucleus. We have neutrons. We can assume they're neutrons in the nucleus. Instead of saying positive particles, let's go ahead and call these protons. And then we have electrons around nucleus. One thing that doesn't fit accurately is we have too many electrons in first energy level. That first energy level only holds 2. One way it could be improved. So 2 electrons in first orbit, and we would have, let's see, 1, 2, 3, 4, 5. We'd have 5, because we have 7, I believe. Yeah, 5 electrons in second orbit. So we would need 2 orbitals. All right, next one here. Wow, we have lots of different energy levels. Several energy levels, each with the appropriate, I can't spell, appropriate number of electrons. Of course, we have all the other stuff as before. What's wrong here? Well, we know that the electrons don't orbit in perfect circles. So how could we make this better? Well, we could show electrons in regions of space where they could be. So remember, we don't know exactly where the electrons are, but we know where they could be. And then the last one, this is our electron cloud model. So electrons in regions. Really isn't anything wrong with this. So this is the best model we currently have. So I can kind of make that the answer for both. And that's it. That's a study guide. That's everything we covered in Unit 1.